Okay, hello everybody. This is CUDA and Open Lab seminar on April 15, 2024. And today we have a lab encounter. And with great pleasure, we welcome Yusuke Sugano of the Interactive Visual Intelligence Lab of the Institute for Industrial Science at the University of Tokyo. It's a lab encounter, so there won't be one presentation, but some. And so basically, this is a really cool kind of coincidence because it's another nexus that is related to computation, computer networks, artificial intelligence, which is not in our case cultural analysis, but in this case human-computer interaction, which we all need people to think about because there's good and bad ways how to do it. Actually, one of our PhD students, Tilman Ohm, is currently with Yusuke in Tokyo. So this is sort of like an encounter of an encounter. And we ourselves are spread out. So this is sort of, really neat coincidence over half the globe. One thing that we should sort of maybe like, there's usually, we don't have any strict guidelines in terms of format. So lab encounter, we have a 2-hour time slot, and the stage is always the stage of the guests. So you can do presentation and then take questions or take questions in between. We can be shorter if you like. And so the kind of key thing is like sort of to make this as flexible as possible while sort of have mutual inspiration going on by we are all ears and we are here to ask interesting questions and vice versa. So with that, I will give the stage to Yusuke, who's already tried out the slides, and let's take it from there.
Okay, yeah, thank you for the introduction. It's great opportunity to give a kind of overview of our group. And I have another 3 presenters today. Eirin, Jae, Wataru. Eirin is a postdoc, and the other 2, Jae, Wataru, are PhD students. And in the beginning, I will give some overview talk. And afterwards, I'm planning to give 3 of them to introduce a bit more details about their own researches. So maybe we can have Q&A session in between, right? Maybe.
Sure.
Yeah. Okay, then, shall we start with right. So again, thank you for the introduction and for this opportunity. We are Interactive Visual Intelligence Lab working at the Institute of Industrial Science, the University of Tokyo. So many logos, but I'm an associate professor at the institute. And basically, as introduced, our research interest is in between computer vision or artificial intelligence and human-computer interaction. So our central research interest is how can we achieve some sort of interactive, intelligent interaction between the humans and the computers or robots based on the images and the videos. But maybe later, as we introduce some other researches, our key interest is also shifting towards multimedia. So it's not only about videos, images, but we are also interested in other modalities. But anyway, I think our key interest is how to bridge this intelligent computers or intelligence robots and people, users, in the intersection of machine learning and HCI or interaction design, I would say. And this topic, I think, involves a lot of different aspects, I think. For example, it is also, our central research theme is vision-based human understanding. In order to achieve this goal, like intelligent interaction, video-based interaction between humans and computers, of course, we need to give computers ability to see and understand how humans are behaving. And when I was a PhD student, I was even interested in, for example, the task of gaze estimation, eye tracking, using videos. So this is still a quite challenging task, but if we can transform computers into a kind of eye tracking machine only with cameras, we can use this to design more natural interaction between humans and machines. And recently, we are also interested in how to get users involved in this kind of machine learning process. So in a global term, I think this kind of human in the loop machine learning is quite nowadays becoming more and more important, in my opinion. And instead of providing kind of pre-trained models to end users, we are basically interested in how to get diverse populations involved in this kind of machine learning process tailored for individual people and users. And of course, on the application side, it is also important to design more user-adaptive systems, like how to adjust the behavior of computers or machines according to the desire of or need of users. And nowadays, I think it's also important and becoming also popular to provide, for example, give humans ability to generate, for example, images according to their demands. This is also an important computer vision task. And actually, today I'm not going to talk about details, but we are also interested in how to design the system that allows novice users to, for example, generate images. So understanding images is also important, but generating images is also important. So yeah, this is of course, the 4 examples is just a toy example of the aspects of this intersection between computer vision and HTI and machine learning and machine and humans. But the important point is, I think they are not clearly separated in some sense. For example, enabling this kind of vision-based human understanding is, I think, quite important to design user-adaptive system or visualization system, because if computers can also understand our natural behavior or nonverbal signal using cameras, it also enables a more natural way to provide a user-adaptive UI and visualization. And also these 2 things, like human-in-the-loop machine learning or interactive machine learning and user-adaptive computer vision systems, is also related to each other. I think design philosophy could be quite similar, while the human-in-the-loop machine learning is more on the machine side, while the user-adaptive computer vision systems are more on the user side. And instead of creating distinction between these different aspects of this target of designing intersection between computer vision and human-computer interaction, we are basically interested in covering these diverse areas by conducting multiple research projects. So this is the overview of our interest. And for example, as I mentioned earlier, I have been interested in doing eye tracking and gaze estimation, especially using cameras. So as you may know, the eye tracking itself has a long history, and there have been historically a lot of people trying to make eye tracking devices and trying to investigate eye tracking applications. And for example, of course, as a kind of measurement of human attention, many people in the advertisement or marketing industry have been interested in measuring our attention on, for example, advertisement. And also, it has been quite an important topic to design a kind of gaze interaction techniques, historically speaking, especially for assistive technologies. If the user cannot use their hand or other input modalities, maybe eye gaze input can be a great modality for people with some disabilities. And recently, I think this gaze input is also becoming quite important in the context of virtual reality. Like as you may know, Apple Vision Pro involves the eye tracker inside, and they actually designed a very well designed gaze interaction. Which has some basis in previous literature on the gaze interaction researches. But eye tracking community actually got excited and surprised how they well integrated this kind of techniques into the natural user experience in the virtual reality headset. And also another important direction is how we move our eyes provides a very valuable information to understand our internal states. And also this is related to medical diagnosis. Like there have been a lot of researches about using gaze information for diagnosing kind of a developmental disorder, right? So yeah, using this kind of eye tracking gaze information can also provide a valuable information to understand users or humans. But historically, there have been a lot of eye tracking devices, but it is still quite challenging to perform eye tracking only using webcams or ordinary cameras. And later, Jawei will also talk about more details about this, but yes, I have been working on this camera-based gaze estimation. So frankly, casually speaking, this is a deep learning-based gaze estimation. We collect a lot of training data that consists of human faces and gaze directions. Gaze direction is annotated as a 3D vector. And basically, we train some deep neural network that takes face image as input and output gaze directions. So yeah, it has been challenging, but somehow community knows like if we can have a good quality of data, good amount of quality of data, we can train our gaze estimator with reasonable accuracy, which already enables a lot of different application scenarios, I believe. But still, training data is really difficult. Like obtaining training data for each person, each environment is extremely difficult. And without good training data, the performance actually still not enough to achieve real world applications. And yeah, as I said, Jawei will also talk about this kind of technical approaches about how to bridge the gap between training environment and test environment. And we are conducting very, pure computer vision researches regarding this. But the point is, of course, we can develop a lot of different computer vision algorithms to achieve this goal. It is always still not quite perfect. I mean, only addressing this issue of the domain gap, environment gap of training data and test data is fundamental issue for this kind of machine learning based approaches. And even for research, we still need more data. In this case, data involves face images annotated with ground truth gaze directions. This is really costly to achieve actually. So yeah, we have been also working on dataset creation researches. And recently, one of the key, my interest is doing some sort of taking some design approaches to address this task. Like we researchers want to collect a lot of face images, which is extremely privacy sensitive. And together with ground truth gaze position, we need to know where the person is looking at when we capture the face images. This is a huge requirement actually. And usually people don't want to expose their faces to the data collection pipeline. So yeah, we have been kind of struggling to collect more diverse data. And it causes a kind of bias in the model. Maybe current existing gaze estimation models are slightly biased towards maybe computer science students in the world, which involves more Asian students, I guess. And yeah, there is definitely a bias in the gender and age in the training data set, which of course means the model cannot perform well for some populations. So our idea in this project is we want to make some gamified system for collecting training data for gaze estimation. So in this video,
アイコムはゲームやワークショップを通じ
narration
て
is anyway
一般の人
Japanese,
々と
but
研究者が AI について対話し一緒に開発するための新しい仕組みをデザインするプロジェクトです。
so yeah, we
一
want
般
to
の
design
人
some
々が
sort of
楽しんで研究に参加し AI について学ぶ機会を提供しながら研究者側も同時に AI 研究に必要なデータを獲得することができます。
私たちは一方的に個人データを収集するのではなく、人工知能技術の紹介や技術活用のためのワークショップを通じて、一般の参加者とコミュニケーションを取りながら未来を共に考え
the sound of the video is covering your own voice.
Okay. Maybe then I think better to go without sound. Can I share it again?
Okay.
Yeah.
Excellent.
Right. You can still hear my voices, right?
Yeah, I can hear you. Yeah, we can hear you.
Yeah. So what I said is, yeah, we want to design opportunity for both researchers and public audiences to both think about the potential, potential outcome of this kind of AI and gaze estimation research. And also, at the same time, we are also interested in gathering data, which can be used as a training data for machine learning or AI systems. And game flow is like, game is designed like, this is a kind of game played by two players. And the task is one player needs to guess the word pointed out, conveyed by the other player using gaze as a modality. So one player knows the whole word. In this case, tamanegi is an onion, four-letter word in Japanese. And the other player only knows the part of the word, basically. And this missing word, this red player needs to tell the other player using their gaze. And basically the answerer player needs to guess where the character location is. But actually identifying a single character using only gaze is quite difficult. But with rough locations as a clue, basically the other player could guess the whole word that makes some meaning in total. And the point is, in this case, the player telling the character to the other player, like a red player, in this case, the system knows which character the questioner user is looking at. And if we capture the faces together with the correct word location, we can collect some sort of training data for training gaze estimation models. Again, the goal of the gaze estimation is to find the mapping between the face image and the word gaze location, right? So if we can train a model to guess the character based on the faces, this means, practically speaking, this means we can train some gaze estimation model. And we are also, this is just another video where we provided this game for at the kind of science museums. We are kind of collaborating with a science museum in Tokyo, which is something Wataru will also talk about later. And in this case, we use this game as a kind of media for museum visit by deaf school kids. So basically, they are living Japanese sign language, and basically, their primary language is sign language, and basically, Japanese language is a second language. And but because this game does not rely on any sound, we could provide an experience of this kind of gameplay experience, and we could also communicate about the implication of using computer vision machine learning or gaze estimation in a scientific context. So without this kind of game design, I think we could never have such kind of opportunity to talk about gaze estimation technique with public audiences. But this kind of approach, designing some gamification experience for machine learning in general is, we believe, quite a promising direction for both data collection and kind of social development of machine learning AI models. And one of the reasons why we are interested in this kind of gamification is, as I mentioned in the beginning, we are also interested in providing some human in the loop or interactive machine learning systems so that we can get more diverse people involved in the development process of AIs and machine learning systems. And our intention is only discussing about the future of machine learning is usually not enough. And sometimes it's extremely important to have more opportunities to develop something together. I mean, having a joint opportunity between researchers, developers, and generic audiences to develop some prototyping, some AI systems is, I think, quite effective and important opportunity. And we have been working on kind of as a context of research project which aimed at using AI and machine learning for accessibility. Like, for example, how we can design a computer vision system for blind people and how we can create a sound recognition system for deaf or hard of hearing people. And sometimes we researchers, machine learning researchers, try to design such kind of system, but we believe it's also quite important to get people with disabilities themselves as kind of stakeholders in this development process. And for that kind of communication, we believe creating something, prototyping some AI systems together is key ingredients for this kind of communications. And yeah, we have been working together with the Science Museum to provide, for example, some hands-on events of machine learning systems with museum visitors, which, yeah, Wataru will also talk about more details. And yeah, we are aiming at designing some more opportunities for novice, non-research people to create their own machine learning or AI models. And maybe if I talk about this project alone, maybe it sounds like a totally different opportunity, totally different research direction from gaze estimation research, but at least in my perspective, everything is kind of connected. Like we are interested in bridging the gap between machine learning, our machine and humans, and the machine learning research and HCI research. And yeah, I hope the other three talks will also provide a bit more details about our perspective. And yeah, this is the last of my slide. And yeah, please ask me if you have any questions.
Thank you very much.
Yeah, presenters, yeah, these three. Okay, thank you.
Thank you very much. Should we just continue or should we take questions in between?
Maybe, yeah, we can have a short Q&A before going to individual talks, I think. Yeah, of course, yeah, details about the individual researches, maybe you can keep it, but if you have any comments, questions about the overview, please.
Yes, so the maybe one interesting question, like HCI is sort of like a twofold thing, right? Which is at the same time producing research publication, but you very tangibly typically makes things better. Right. Meaning there's patents coming out and then this is implemented in objects. So is there, what is your balance regarding this? Are you more aiming for concrete applications or is it like, how much is it sort of like blue sky research, if you would call it?
I see. In that sense, ideally, of course, I would say we want to do both, but in some sense, I think, for example, as a person working at the university, we are not really good at creating, for example, product level something, right? So at least our aim is more on, how to say, at least I would say, because we are also doing collaboration with Design Lab at Tokyo IIS, we are basically creating, interested in both paper writing and kind of doing some, I'm not sure if I can say design research, but creating some prototype and check if this prototype works with actual audiences. But in some sense, yeah, both aiming for a bit more academic direction. And honestly speaking, I think I need to find more industrial partners to do more practical implementations. And yeah, that's something I want to seek in the future.
Nice. Mila Oiva has raised her hand.
Yes, thank you so much. They sound super interesting, and I can't wait to learn more about what you're doing in your lab. I just wanted to ask if you could very briefly describe how does it actually, this kind of like co-creation with members of the wider public, how does it actually work for you? Do you usually first, for instance, introduce somehow like how machine learning functions, and then you discuss how it could be applied for their particular needs? Or do they kind of like come to you and with some specific questions? Or how does it actually kind of like come up with this? Because I really like this idea of co-creation of things. Thanks.
I see. Yeah, honestly speaking, at the moment, what we are doing is basically, in some sense, we are doing research about how to create this kind of co-creation opportunities. So yeah, it's kind of complicated, but yeah, our research interest is at the moment on more meta aspects of how to create such kind of opportunities for co-creation. And of course, we are hoping this can also result in more concrete research projects with diverse populations. But at the moment, of course, we are, say, for example, sometimes we conduct some workshops or exhibitions, and there have been a lot of interesting discussions actually with participants. Sometimes participants come up with a very nice idea, which actually has some prior work. This is actually great. Like some people just come up with, say, image recognition tasks, new image recognition task, which actually has been already studied with some other university groups, not the product level, but in a research paper level, they exist, which is actually quite interesting to me because if I, for example, ask grad school students to come up with new ideas, they usually struggle with finding new ideas, right? But sometimes, yeah, discussion with no public audiences can provide a good ideas, and I see some hope there. But yeah, honestly speaking, we haven't yet settled down to a concrete research projects with, yeah, actual, yeah, non-research people involved. So yeah, that's also another important future work for us, actually.
Mark Arnett.
Hello, very inspired work. I'm also having interest on eye tracking. In fact, my artwork is using generative AI, and with eye tracking, it regenerates the areas that you look, and it's been published already. My question was more like, did you collaborate with artists? I actually did my exchange in the MA studies were in Yamas University in Yamaguchi, where the more prominent new media artists in Japan had come, like Daito Manabe and my friend Kanoso and several other. Did you collaborate not only with designers but with artists? Because I think your research could collaborate quite well with them, and probably this kind of enter into other type of people through exhibitions. And this co-creation is the same as interactive art in a way, you know, like interactive art, you let the audience to kind of create one part that you don't do. With the interaction means yeah, I don't know, I mean, I'm an interactive artist. I do a lot of interactive art, and I know quite the people who do this in Japan, and definitely it's quite an interesting match that you could do with them, I think. I mean, also with other artists like I mean, and with the eye tracking, we actually I used to work in Ars Electronica. I don't know if you know Hido Awa, who is now the lead of the Feature Lab. I used to work there, and actually my first eye tracking things were in the for Ars Electronica museum.
I see.
And it was actually a collaboration with scientists and Ars Electronica to gather data, actually, exactly like you were saying. We were gathering data for some research projects. I'm talking about 2009. It was 10 years in the main hall of Ars Electronica. Later on, now there is more about AI, actually. You should talk to Hide probably, and he just now is directing the Sapporo Biennale, but he's also all the time in Japan doing collaborations.
Yeah, so answer is no, I haven't done it yet, but yeah, I would definitely want to do if I have a chance. And I actually have some friend in this new media art field, and I usually don't explicitly talk about this episode, but do you know iWriter? There was a project for using
actually, no, I know, yeah, Zach Lieberman and also and Kyle McDonald, and I think Daito was also involved. Yeah.
When I was a grad school student, maybe master student, I actually had a chance to communicate with them, like Zach, Kyle, these people, and this was actually huge inspiration source for me to do more eye tracking research. And
Oh, great.
yeah, that was actually a source of my academic journey. But at the moment, I haven't done any artwork. I mean, yeah, close collaboration. And yeah, so yeah, that's, and I have been, for example, I have been discussing with another artist friends about how to enable, like, how to say, how to understand our behavior about, yeah, perceiving artworks. And if we can create a machine that can see the artwork, or maybe a machine seeing audiences, seeing artworks, like this kind of, yeah, how to say, mutual relationship of seeing and being seen sounds quite interesting to me. And yeah, definitely, I'm personally interested in. And if other students, for example, is interested in doing something in this line, maybe yeah, we will do it. And of course, we are always open for collaborations. At least, yeah, I am. So yeah, this is yeah, yet another important future work for me.
Great.
Super nice. I have one, maybe, it's interesting. It's a follow-up question, but it's like sort of like going way back in time. One interesting that sort of I realized, like looking at your field of characters that you use to do eye tracking. Obviously, this is sort of something which is very Japan specific, because obviously in Western languages we got 26 characters in an alphabet, so you got less characters to do stuff.
Yeah.
But that brought up something in my mind, which I think is quite interesting to consider, which is that Japan has a really, really long tradition and really, really good user interface design. So, pottery goes back 2,000 years. The same, when Walter Gropius came back from, actually wrote a postcard back to his fellow architects at the Bauhaus, well, was it in Katsura? He said like, oh, we're 300 years late, right? The Japanese do this since like forever, form follows function. And the same is true for sort of electronic and computer user interfaces, where there was a time when, for several decades, Japan was very much ahead in hi-fi user interfaces, computer user interfaces, musical instrument synthesizers, like all that kind of stuff. And so one of the interesting things is, though, that like Germany and the US in some respect, we're like these industrialized societies who went through a kind of saturation. Like there's so many things we produce that at some point there's a kind of way of doing it, right? Like, so there's like basically we're not a blank slate anymore. And in that sense, I have a question which I think is, it's like, in how much are you seeing the work you're doing in that kind of tradition? Because at the same time, you're sort of in this field which seems like only exists since 20 years, but obviously it has a 50, 70 year, whatever tradition, while at the same time, it has these really deep roots, because if you do tools and instruments and so on, I mean, this has been the problem since centuries, right? So how do you deal with this like really massively present tradition of awesomeness in this area in your own country?
Well, yeah, it's difficult question to answer, but for example, I think even in the HCI field, I think Japanese community was quite strong for designing something physical, something tangible. But like on the other hand, I think especially in the recent AI field, Japan research community is, I think, a bit behind, I guess, like developing new machine learning AI technologies are more advanced, I would say. Of course, in the US, Europe, China, and in some sense, yeah, we are trying to catching up, but yeah, still kind of bringing innovative ideas in this field is still quite challenging. And in that sense, recently, I'm also feeling like bringing this kind of, I'll say, a bit more tradition in our culture, like some research fields we are good at, we are already good at. And connecting these two fields may be also quite important opportunity for us, like working at connecting this kind of recent cutting edge technologies into more, physical design or, these kind of things. Maybe, I'm not sure if this becomes the answer to your question, but yeah. that's something I have been recently feeling, and that's another reason I found that designing a physical game for machine learning data collection is actually quite interesting approach.
Mhm.
And this is maybe something, we are hoping maybe we can show some strengths, I guess. But yeah.
Okay, nice. Yeah, thank you very much. Mar, do you still have your hand up again, or is it still okay? Good. Maybe we should continue with the talks, right?
Right.
Okay.
Yeah, sorry, maybe I took a bit more time, but yeah. I will hand over to
That is exciting.
who want to start? Order, maybe Eden can go. Eden, Jawei, Wataru.
Okay, so yeah, let me share my screen. So can you see my screen now? So I'm Eden from the Sugano lab, and thank you for the invitation today. It's a really good chance for communication. Today my topic is hierarchical temporal modeling for human hand actions. So this is related to my PhD research. And so first, let me explain by decomposing this title. So the field is human hand actions. So why study these human hand actions? Because we computer vision researchers, when we develop AI system, we want that this system can help to interpret some human behaviors and intentions. And also we want this AI system can interact with our human subjects. This is kind of critical for several application fields. For example, for the human-robot collaborations. And in this case, we expect that the robot can somehow aid us to finish some tasks together, like in the factories, together assembling some things. And also the VR system. So the AI system needs to locate our human hands and try to understand some instructions conveyed by our human gestures. And also the imitation learning, and also something like teleoperations. And we want the AI agents to try to mimic our poses and to do some things for us. And also AI existence, like we want the AI assistant to observe, to preserve that our human subject's performance, and then based on the performance, give some instructions and suggestions. So interacting with human subjects is important. And in order to interpret our human behaviors and in order to interact with our human subjects, we noticed that starting to understand our human hands is very important. Because we human subjects, we actively using our hands to interact with some objects and to perform some actions. So given these motivations, we study the human hand actions. And considering understanding the 3D hand pose, like to locating our hands, the joint positions in some cover space, and also understanding at a higher semantic level. At our hand movements, the temporal context, it usually encodes some high-level meanings and intentions. For example, like we have some patterns of hand movements to finish the action of a frying sausage. So to study human hand action, the key insight is to model the hierarchy temporal, considering the semantic dependency and the temporal granularities of the hand pose and actions. So the semantic dependency is that action is usually at a high semantic level, as it's usually defined in the form of a verb and a noun. So the verb is depicted by the movements of hand poses, the hand motions, and the noun is usually the object being manipulated. And for the different temporal granularity, so action is usually lasting for seconds, so it has a longer time spans. And hand pose is usually corresponds to an image, so it depicts the instantaneous movement. And we model to exploit all the temporal dimensions, and we build on the very popular transformer architectures. So given the solutions, we first model from the recognition side for the 3D hand pose estimation and action recognitions. And then we extend to capture not only the recognition side, but also to predict the future 3D hand movements. So let me explain by decomposing the two solutions. So first is regarding the recognition side. So the input is RGB video, and here in this work, we constrain on the egocentric view. And our output is hand pose estimation is that for each input image, we output the frame-wise 3D hand transpositions in some cover space. And also action recognition is that for the whole input video, we output its video action category. So the case is pouring milk here. And our motivation and key designs comes from the following aspects. So first, we noticed that if only from a single image, actually for action recognition, it shows severe ambiguity. Like you cannot distinguish whether I will close or open the juice bottle from a single image. And we need to leverage the video, to leverage the temporal context to solve this ambiguity. And also, even for hand pose estimation, from a single image observation, it can suffer from frequent hand occlusion or truncation. For example, the case of porn liquid soup. So therefore, we exploit on the temporal dimension to leverage the temporal information for both hand pose estimation and action recognitions. Second, as introduced earlier, so we noticed the different temporal granularity and semantic correlations for hand actions. So in response, we build a hierarchical model, temporal models. So here is a transformer architectures, and it has two cascaded blocks. So these blocks are with transformer encoder implementations. And the lower post block, it focuses on sub-second time span. So it's a relatively short time span to exploit the short-term temporal queue for hand pose estimations to output for each frame is hand pose and the object label. And in this way, we see that if we leverage the temporal information, it improves the robustness under occlusions and truncations. Also, we show the attention weights, and we see that by constraint on a narrow time span, so we try to avoid over-attending to distant frames. So therefore, by using the short-term temporal motions, we ensure sharp local motions. And the upper block of the cascaded blocks, so it works on the whole video to leverage the long-term temporal queue for action recognitions. And also, we can see that we cascade the action block and the post block to model the semantic dependency. So therefore, the action block, it derives the action video given the input pose and object label predicted from the pose to model the semantic dependency. And also, this is a case showing that we are able to effectively exploit long-term temporal queue for action recognition. So here we have a demo of taking out expressos, and actually this action can only be judged by the last few frames depicting the process of taking the capsule out of the box. And we observe that correspondingly, our action block gives the most attention to these keyframes for the action recognitions. And also some qualitative results for hand pose estimation. So we respectively train and test on two very popular first-person datasets. So first is FPHA and then it's H2O for two hands. And because computer vision paper and we work on some established tasks, so we compare with existing works. And we show state-of-the-art performance, like considering the accuracy of action recognitions. And also here we show the accuracy of pose estimations. So we outperform the existing baselines. And also on the H2O datasets, so we show better accuracy for action recognitions. And also we show less error for the hand pose estimations. And then we extend to concurrently capture both the recognition side and motion prediction side. So here, besides asking the 3D hand pose and the action category for the input observations, so we here extend to further predict also the 3D hand pose sequence for the future timestamps. So we formulate by considering the following aspects. So we first notice the temporal regularity shared across the observed timestamps towards the future timestamps, considering both the short-term motions and also the long-term action consistency. For example, so this example is showing like the hand reaching to a chip can, and one can know that the guy is about to take out a chip, and then he will guess that probably the guy will grab and pull out the chip to complete this action. So this is a case of temporal regularity. In response, we build out the generative model to capture this temporal regularity. And with this temporal regularity, we jointly modeling both the recognition and prediction tasks. So generative models, they have encoders and decoders. And the encoders encode the input for the recognition tasks to output the frame-wise pose and the video actions. And the decoders fulfill the generation tasks to generate for the future 3D hand pose sequence. And furthermore, given the observation of the temporal granularity and semantic correlation for hand pose and action, so similarly as previously introduced the hierarchical temporal transformer. So we also build the block cascades, but with the generative models. So similarly, the lower one, it focuses on a short time span to exploit for hand pose. And the upper one, it works on a long time span to leverage the long-term temporal cube to exploit the actions. And additionally, we introduce a middle-level feature. So this middle-level feature, it encodes a sub-second hand motion. So it's a clip-wise features. And we can see that this middle-level feature is from the perspective of architecture, it bridges the two blocks. And also from the semantic and temporal hierarchy, it also bridges the hand pose and actions. And this introduction of middle-level feature has several merits. So first, it enables training flexibility. So the lower block and the upper action block, they can be trained separately so that we can reduce the computational requirements when we train some very cumbersome models. And furthermore, like the post block is detached from the action. So when we train the post block, we can leverage train data without constraining the availability and the transitions of action labels. Second, with the middle-level feature, we actually decompose the pose predictions into hierarchical subtasks so that we can better capture the short-term regularities with the post block and the long-term action continuity with the upper action block. So for experiments, we train ours on related baselines by combining different hand pose and action datasets. So with different scenarios and with different accuracy of pose labels. We show that in this way, the joint modeling of recognition and prediction benefits. For the prediction side, we compare with a related baseline. So this baseline models only the prediction side. So it conditions the motion predictions on some given ground truth actions. And we can see that the comparison shows that we enable plausible motion generations over time. Let me illustrate by considering a demo. So first I show the sequence, and now I show the ground truth for the predictions. And then I compare the post-GPT and our proposed generative HTT. And we can see that the joint modeling enables us to learn strong motion action regularity across diverse training motions. And our generated motions can better capture not only the global action guidance, but also the local motion continuity. When previously introduced the HTT as a recognition task, we demonstrate the benefits of modeling the semantic and temporal hierarchy. So here for the discussion on the prediction side, so with the actions and with the middle level feature, we can see that we enable the generations to better preserve the global regularity. Also, the qualitative analysis demonstrates our benefits of using the action-guided predictions. It enables more realistic generations. And also the introduction of middle level, it enables competitive quality, but the result shows better diversity. So the concluding remarks, we study in the field of human hand action modeling, specifically to understand the human hand pose and the semantic actions. And our key design is twofold. So first, the core is to build theoretical temporal modeling so that we can faithfully capture the semantic dependency and temporal granularity for hand pose and actions. And then also in the second half, we extend to build our generative models to capture the temporal regularity shared from the observed timestamps or the future timestamps, so that we can jointly and better modeling both the recognition and predictions. For the future work, first is basically our discussion is related to the hand pose and action. So we do not focus that more on the objects. But still, object is very important, as I said, in the applications for something like imitation learning, for something like human-robot collaborations. Object plays a very important role, especially considering that actually the hand motion can indicate the object affordance, and also the object can also benefit the hand pose estimations and hand motion predictions, as probably like for hand motion predictions, the object can suggest the goal of the future hand motions. And also we noticed the chance for interdisciplinary studies. So especially for robotics, like efficient learning for robotic manipulations is currently very hot topics. So especially we have internet scale human video data, like from our human demonstration, whether the robot can learn to manipulate objects and interact with the surroundings. And also, I found very inspired from the discussion with Tillman. So hand pose and gestures not only conveys the temporal semantic actions, but also they may convey some metaphors and meanings that are related to the cultures, personal habits, and religious belief. So this can benefit, for example, interpreting some artworks and some cultural behaviors. So let me finish. Thank you for listening.
Thank you very much. This is great. So, yeah, thank you. This is amazing, actually. If there's no hands raised, I may ask the first question. Okay, so Mila, go ahead.
Yeah, I actually don't know where to start because I find this super interesting, fascinating work. I come from maybe from totally different disciplinary background because I'm cultural historian and I work mainly on historical audiovisual materials. But I find all your examples very, very invigorating and super interesting. And I kind of like have two, I don't know, questions / comments. First of all, as you already mentioned, like gestures are, of course, they are culturally dependent, and also they might change in time. What we have found as certain gestures meaningful in certain ways in like 50 years ago might be different also today. So, but analyzing and understanding and detecting these gestures also in like historical audiovisual materials is super interesting, and I know that there are some developments, but not of course yet as kind of like super developed. So that's very interesting. And I found super interesting what you said about this kind of like how you use temporality as kind of like for understanding what does the gesture mean and what is the actual kind of like meaning of certain gestures. I wanted to maybe ask if you have kind of like used some wider contextual information regarding the meaning of a gesture. I mean that kind of like whether a certain gesture is taking longer than expected, or is it shorter than expected? Just to give you an example of a handshake, we have a certain expectation that if I shake hands with somebody, it will take, I don't know, 1 second. But there are kind of examples of the US ex-president Donald Trump shaking somebody's hand too long in a way, and it's already kind of like a super weird. So these kind of like, so the temporality has also these kinds of meaning. So if we understand that a certain gesture should take X amount of time, so if it's too long or too short, it might give us some interesting feedback. This is, of course, this is very detailed question, but I'm just super interested in your work. Thanks.
I think it's very interesting. Like, yeah, like in my field, it's kind of related. Like, we usually to check whether a person spending how long the time on some specific task or continue some gestures to see whether the person is professional or not. Yeah, so I think this is kind of related. Like, yeah, different people have different patterns. And by considering how long the gesture or the action lasts, and whether it has some meanings for showing something like a personalities or showing something whether it's professional or not, I think it's very interesting. And yes, it's also personally very interested, and probably a very important future work.
Excellent. Thank you very much. I have sort of 3 questions. There's one here. Xenia Mokina asked a question before because I asked questions before. So Xenia.
Yeah, I have a small one. I think on
Hi.
your slides you showed the results of your object detection, and there was like 2 numbers for left hand and for right hand separately.
Yes.
And I think your approach wins like in some cases for left hand. And why do you think there is a difference in accuracy for left hand and right hand? Is it because of in the data a lot of people are right-handed, or maybe left hand is just harder to get?
This is also a very interesting question. Like my supervisor also asked me about this. I think it's related to the data. Yeah, like as you say that most people are right-handed. So when they're doing some tasks with both hands involved, the left hand can be more stable. So in this case, like leveraging the temporal, it's just simply smooth, so it can benefits. While the right hand is more with drastic movements, so probably more chance with errors.
Nice.
Cool, thank you.
Nice, this is great. The related question, you had this, so you had things where you obviously do recognition of the pose of the hand from the frame itself, but then you also had this sort of mocap device with sort of like wires where you actually measure not by computer vision, but by sensor. Is that true? Or so how does that?
So you mean about data collections or?
Yeah, so is it like how much of what you're doing is motion capture with this sort of like physical device, and how much is that like basically from the frame? Because you have shown a lot of things like opening the bottle. You really don't, you cannot see the hand very much, but the wires give you obviously full information, right?
So the wire is basically used for like collecting the ground truth for training and for evaluations.
Okay, okay. So basically, your research, you use computer vision, but the tracking with the physical devices sort of for ground truthing, basically.
Yes.
Okay,
yes.
Interesting. I have a like this out of curiosity. We once measured hand gestures in Baroque paintings, and one of the interesting things we found out is that there is most of the gestures actually coincide with a catalog. Like somebody wrote a catalog of gestures in Baroque paintings in the 17th century, and most of the gestures actually appear in that catalog. But there's some that are not appearing in the catalog. But the most striking fact with the frequency of gestures is exponentially distributed in these paintings. So a lot of people point, a lot of people adore. Very few people are desperate, but they all have meanings. Like somebody wrote a label of like, okay, this means somebody's desperate, for example. You know, it's like, which now we wouldn't agree either in the West, right? So now here's the key thing. Like this is sort of like raising a question. Like if there is indeed an exponential distribution, it by necessity means that not only the machines are better trained in the frequent gestures, but also us, because like if you have orders of magnitude more exposure to pointing, then this is sort of much easier to recognize than I don't know if somebody makes this, right? Which if you haven't seen Star Wars or Barbarella, you don't know what it means. And if you saw both, you don't know what I'm quoting. And so the question is that sort of something you encounter? And let me extend it. How about gestures that you encounter for the first time, which as a human, I may think that's the most important thing. Like, you know, basically every gesture I have made while asking you is sort of known. But if I make something that's like for the first time happening, it's by necessity not in your catalog. It cannot be recognized. It cannot be predicted. But it's the one thing I really want to see. Like, how do we deal with sort of like the canon growing beyond what you train your machine to recognize, basically? Do you have an idea of what the corpus of all possible gestures is? That's maybe the shortest version to ask the question.
So being that if we have made a gesture that never been seen or never been trained before, how do we handle it?
Yes.
This is also very interesting, I think, probably related to also the research interest of Sugano Lab. Yeah, like how to handling or how to recognizing this kind of things is important. Yeah, so I have to say that it's important and open challenge, probably.
Nice. Yeah. I'm bringing it up because in a sense, your cultural religion question is, you know, like sort of classifying stuff that is encoded, which religion very much does, is one thing. But if we say, let's take all of YouTube and say, what's a catalog of gestures that actually appears? If we approach it from the catalog perspective, we may recognize a subset. If you approach it from, say, another hierarchical perspective, where we say, okay, humans have 4 appendages, of which 2 are hands, and if I can do body pose recognition, I obviously can guess which of the 2 appendages are hands. And then I have the catalog of all hands that are on video. And then I can actually produce a new catalog of gestures. And I think coming up with the new ones is probably much more interesting. It's similar to music, right? Like it's sort of
Yes.
trivial to recognize blues and rock and roll and hip hop. But if we would recognize all the hundreds of genres of music which we don't know that they exist, that would be really, really cool. So yeah, this is very fascinating, actually. Thank you. Yeah.
Yeah.
Should we go on? We should.
Yeah.
I think it's better to have some time for discussion at the end and let everybody talk so we don't run into time issues with the last talk.
Yeah.
Thank you, Ian. This was amazing.
Oh, thank you so much.
Okay, so maybe I'll begin this one.
Yeah.
Yes. Okay, can you see the screen?
Yes.
Yes. Okay, thank you. So my name is Jiawei, and I'm a third-year PhD student at Sugano Lab. So I'm also doing something purely in computer vision. So I'll omit some technical points. And my research is about using synthetic data for gaze estimation. And you've seen this video just now, which appearance-based gaze estimation is just estimating the gaze direction given this input, feeding it to some deep learning model, and the output is just a pitch yaw value, which represents the gaze direction. And why it's 2D, I'll introduce later. So the existing challenge for gaze estimation is that the data set is really not enough, because firstly, obtaining the gaze label is very inherently difficult, because you have to ask the person to look at some points before they takes the picture. And in this case, another data set, and you have to ask all of these subjects to look at some predefined point such that you can compute the vector from the person's eye to this target. Then you cannot just annotate some gaze label to some existing images. Another thing is that there are huge domain gap between each data set. Here are 3 example data sets. Well, the first one is that they collected this data set during their daily use of the laptop. In this case, they use iPad. And in this case, which is the previous video, and yeah, they use a lot of cameras, and they collected this data set in a lab. So they have very wide range of the camera viewpoint. You can see, compare with these two, which are almost frontal. And the domain gap here is the lighting condition, the number of persons, and the head pose. Before going on, let me briefly introduce there's a normalization process, which is almost phase alignment, just crop the raw image so that the input to the deep learning model is just this cropped one, and there's an extra row axis cancellation. So after this normalization process, there's only pitch and yaw. The row axis rotation is canceled. So in this case, the 4 eye corners are always in the horizontal line, which reduce some redundant variables and improves the robustness. So all of the training data looks like this kind of cropped images. And to see the difference in terms of the head pose and the gaze range, here are some distribution in pitch and yaw, comparing these 6 data sets. And this X case, which is this green one, has a very large range of the label compared with other smaller datasets. However, a larger range cannot guarantee high performance on different test dataset. For example, this is the training data and this is the testing data. You can see, even though this X case has a very large range, the performance on this case capture is worse than this MPI. And there are a lot of factors influencing this performance, and we just found it's really hard to collect a real data set to cover this kind of problem. So we turn to use synthetic data. And our idea is pretty simple, just create some synthetic data and augment the case estimation model. To create the synthetic data, there are a few line of works. For example, using, this PowerPoint is always automatically, the 3D phase reconstruction and this kind of gaze redirection using learning-based method. This one is purely photometric, so we can guarantee the accurate label, but we cannot control, like, for example, the separate movement of eyeballs. We can only change the camera viewpoint. And in this case, we can use some, for example, GAN model to generate some images that change the eyeballs or move the head pose, but this cannot guarantee their labels are correct. So in this work, I'll only introduce, we created datasets using the first 3D face reconstruction. The input is like this frontal image, and we reconstructed to 3D space and just rotate it, or you can also say we put different cameras, and so that we can get different images with a very larger head pose range. This is just the details of how we do the face reconstruction. We just use one existing method, and there's a challenge that we have to keep the original label, which is in the physical space, but the reconstruction is actually in a pixel space, which is just based on this input image. So there's this projective matching, which is just the approximation of the camera projection reverse process. I'll skip the details, but you can think we have the 3D face in a physical space, and the labels are accurately preserved. So we create synthetic data with extended angle range. So this is the previous distribution of the real data set. And here we start from the MPI gaze data set, which is this one. And we start from here, and we rotate the face to larger distribution, which is like this. This new data set, we call it MPI-NV, and we use this to train the model and test on some difficult testing data set. And yeah, this is training data and this is testing data. The model is simply ResNet, which is the very basic model currently. Well, there are not here are the results. These numbers are just the angle between the predicted vector and the ground truth vector. So the smaller value represents the better accuracy. And we can see by comparing these two rows, originally this data set can only result in a very large phase error, 30 degrees. And by using the synthetic data, we reduce the errors to a very large extent, and it's better than some real data set like this case 360. Another problem is the synthetic real domain gap, and I'll introduce another model with so to show the synthetic to real domain gap, I'll use these examples. So we use the different reconstruction methods which vary in their quality. And we compare these 4 reconstruction methods and these real methods, and we test on the same data set but different persons. And in this case, the difference between the performance is only due to the domain gap. And the first 3 rows are the single view reconstruction. And their qualities are almost similar. And since this X-case dataset, it contains multi-view images, so we also compared the quality of the multi-view reconstruction. So visually, you can see the single view 3D face reconstruction has a very low quality, while this multi-view one is much better than this one. And yeah, this is just a larger image. You can see the difference between this multi-view one and this single view one. And the multi-view reconstructed image, they are very close to the real images. And we use these dataset as the training data. And here are the results. The first 3 are the single view synthetic dataset, and these 2 are this is the multi-view and this is the real. You can see, even though we use synthetic dataset, this high quality one almost reached the similar performance as the real dataset. However, we cannot guarantee we always have this multi-view source dataset. It's just a coincidence. So to bridge this domain gap, there are 2 ways. The first one is just making the training data more realistic. There's a previous work, they use a refiner to make this synthetic image more realistic, but then the label accuracy will still be harmed. So instead we just do an adaptation on the pre-trained model. The model is first trained using the synthetic data, and then we adapt the model to the target data, target domain, using some target samples without using their label. And since the target domain label is not accessible, so we leverage some self-supervised learning, and in the idea of using pseudo label. And to make this adaptation possible, we need a more stable and domain invariant representation learning. So we first disentangle the different features, and we do the adaptation only on the gaze features. To disentangle these different features, I mean, we separate the appearance feature from the head and gaze. To achieve this goal, we shuffle the appearance feature and reconstruct the image. So you can see the feature in this feature swapping process. We swap the appearance feature of this person with this input image. So the resulted images, this one has the same head pose and gaze direction, but the face is swapped to this one. And for this is similar. So it's just a swapping face. And we need some subnets to help this process. And yeah, it's just we train the model to achieve this disentanglement, and then we do the adaptation only on these case features. And this is just a simple self-training. This is target domain. We don't have label. So to get some pseudo label, we just segment this face and change the background, or we flip this image, which of which the label is also flipped. So we use these images and feed them into the model and get a pseudo label, and we compute the loss between these two predictions. And these are the results. The first row, not the first row, the first block is only using synthetic data, which is after this disentanglement process. So this one, this method shows the generalization process. So and after using some real data for the adaptation, we can see the self-training shows effective adaptation to all of these testing data sets. Yeah, and so yeah, watching these gaze angular error is not very interesting. So I have this gaze demo from which is used our model, and yeah, this is just a demo. And yeah, in conclusion, we saw that synthetic data with this high scalability and controllability is very promising. And in the future work, I think recent generative AI models can further help it. And there are a lot of real world data in the everywhere, but without gaze label. So how to leverage them is also a very important challenge. Thank you.
Thank you very much. Yes, Andres Karius has a question.
Yeah, thanks. So in the very last slide, you mentioned that generative models can potentially make this easier or better. Have you actually tried, instead of, so you described this very, very complicated, very impressive pipeline of figuring out gaze direction, but have you tried just asking a generative large language model such as, I don't know, BLM or Lava or GPT-4, literally just asking what way is the person looking at? Because I suspect that actually probably performs quite well.
Sorry, I couldn't hear very clearly, but is your question like,
let me, oh, that's fine. You want to come on a second, sorry. Yes.
Yeah, sorry, if we're not heard, then just say right away, because yeah. Okay, so large language models, you mentioned generative models on your last slide. So
yeah.
And you have this like very impressive, very complicated pipeline of estimating gaze direction, right?
Mm-hmm.
But
Yes.
I'm asking, have you tried just doing it in a zero-shot manner? So basically inputting an image of a face into a multimodal large language model, such as GPT-4 or Lava or whatever, and just asking what direction is the person looking? Like, what have you tried just checking out how accurate that would be? Because I suspect that probably kind of works and doesn't need this entire pipeline.
Mm-hmm. Okay, thank you for your question. And I haven't done any experiment using the few shot learning using the large language model, but there is another member in our lab who have done that, and I think he didn't successfully doing that. And yeah, I think in terms of the language model, it can basically only shows left up or something instead of a very continuous value, but I think if it has this knowledge of indicating which direction, I think the few-shot learning should work. And here the generative AI models I was considering about is actually the stable diffusion model or something like those kind of image generation. But yeah, large language model is also a very promising direction, I think.
Yeah, it's super nice. Like I find it super fascinating. The key thing is that it's not only fascinating in terms of like the pipeline, and obviously, you know, like Andres said, you could do that way. What you just suggested, actually, Tillman is doing some of the fruit salad work, which I'm pretty sure he will introduce you to or already has introduced you to, is rather similar in that respect, that like, you couldn't sort of extend sort of like the images beyond what you have as a real world sample. But I think I would like to get to something else, like where I wrote down like this is what's really groundbreaking here, I think, is the formalization, because this whole notion of pseudo labeling and sort of coming up with, like, what did you say here? Basically, to have domain invariance is like what vision researchers do a lot, like art historians do all the time. Like since 150 years, we characterize paintings with pseudo labels, like, you know, even style, like mannerism, is not something that exists. Like art historians invented a word for stuff that looks like that, literally. Like people would have not called themselves that way. So that is a pseudo labeling action, which we live with. And the other one is the domain invariant thing. It's like, obviously, you know, at some point you start looking at human poses, which is domain invariant, because like if these humans on paintings of different styles, there is, you know, basically it's sort of the eigenvector of a depicted human as a human body, right? And so one of the interesting things there is that this can be taken to the extreme, like where you could actually ask the question, in how much is any label pseudo? Like in how much do we need labels? And, you know, people fought whole wars about, like, you need to call it this way and not that other way. You need, like, just like our grandmother told us to write with the right hand and not with the left hand. And the same is true for these kind of invariants. There is some which are really straightforward. Like if you go to NeurIPS, the object that is recognized most of the time is a human body, but there's lots of other things. Like what would be the catalog of these kind of invariants? And that is, I think, sort of something where it boils down to. And there, in some sense, it's not just about the question of like, how can what Andres suggests replace what you did, which is true for all of us. Like anything we have done previously without large language models, you can just ask a large language model to do it, and maybe good or bad in doing it. But the question is why? Like why is that the case? Like what is the internal representation of these invariants? What is the function of these labels? And there we have not that much idea, but the fact that you use it that explicitly in your modeling process makes it a really interesting thing to look at, because there in between the cracks, you could actually sort of like tease that out, which I think is really, really, really interesting. Because it's not just like, how can the machine do it better? It's like also, how do we do this? Like, how do you and I do that, right? So that is a really interesting question, because we actually have zero effort doing that. Like we can say, oh, that person looks over there.
Yes, yes.
Tillman.
Well, actually, not really, because the precision of 5 degrees or 10 degrees with which the guys are working is very hard for a human. I mean, with precision of 30%, you can easily do that, but 30 degrees, you can easily do that. But that is quite impressive.
Yeah. I mean, there's this whole research, like maybe, I don't know if you're aware of this, there's this whole research of recognizing the other, like, you know, humans can do that, chimps can do it, birds can do it. They can actually sort of see somebody else of their own species looking at something and then like immediately sort of point to that particular point. So in that sense, I'm not quite sure if I'm with you. I think we're actually pretty good in the degrees, where we're easily doing 5 degrees. You don't think so? That's an interesting thing already. So maybe Tillman, like we have another half hour, so let's give Tillman a question and then like continue with next talk.
Can I just Super quick remark. Okay, so I tried on GPT-4. Yeah, it can estimate gaze apparently based on a couple of images. Just if you're curious.
No,
really?
actually, no, just it cannot actually. Maybe you can notice it's almost always pointing a head pose instead of gaze.
No, I tried with a head that looks to the one side and eyes to the other side.
Yeah, but Andres, what is your label? Because I think we have a different understanding of this terminology.
Numeric.
It's not label as what we understand. Like,
Yeah.
I mean, as much as I understand, we're talking about continuous vectors and not descriptive labels.
Yeah, but you can ask for a numeric value.
No,
Same, it
numeric
works.
value is
Oh, that's
extremely
made up.
difficult. This is actually really interesting part. Like this is one of the most challenging tasks for vision language models, actually.
Nice.
Yeah.
Tilman.
No, this was actually part of this. Yeah.
That was your point. Okay, then let's continue with Wataru, right?
Hey, thank you.
Or more, is it urgent?
Hey.
Well, it was about before, like, is it this model that you are building, you require a big machine or you can run it in an embedded computer?
Yeah, it's quite a light model. It's just
Yeah.
similar to a ResNet. Yeah.
Right.
So basically, you
and
can...
a follow-up question about the ResNet. I mean, are you making the embeddings of the ResNet and then you have an encoder or something to translate from the embedding to get the vector? Because the ResNet is a general purpose image embedding, and how you do it then, that is kind of focused on the eye and not.
The encoder here, you mean here?
Yeah, okay. You have an encoder decoder, and you use for translating this encoder decoder the ResNet embedding. Okay.
Yeah, this is just another way of calling the ResNet, and which I just added another fully connected layer to just make it to a different dimension of the ResNet output. It's almost same as the ResNet.
Okay. And are you going, any one of you, to Seattle to the CVPR conference?
Nope. No.
No? Okay. No, it's because it's a computer vision conference. I thought that maybe some of you had something. Okay.
Okay, Wataru.
Yes. So can you see the full screen?
Yes, just in a second. I just need to enlarge it on the recording.
Okay. So let me begin my presentation. So yeah, thank you for having us. I'm Wataru Kawabe. I'm working on the field of HCI and ML. Especially my interest is to empower the end users, non-expert users, to understand and personalized machine learning. So I basically working on system and workshop design for interactive machine learning. So this time I'm going to present my recent work published in Interacting with Computers. The title is Technical Understanding from Interactive Machine Learning Experience. So as you already noticed, there are a bunch of machine learning services like ChatGPT or Stable Diffusion or something else. So the machine learning models recognize or sometimes generate data around us. They are, of course, sophisticated and usable, but the mechanism is somehow a black box for users. So to make this technical gap ignorable, there's a research field called interactive machine learning. So it aims to facilitate machine learning development by non-expert users by preparing the appropriate graphical or some tangible user interaction. So the point is to design the interface part to bridge the technical gap between the user and the IML application. So the IM system supports some data creation training and validation. So the right bottom one is one of the examples. This kind of user-friendly, easy to understand GUI or tangible device is used to, bridge the gap. But recent IML works has some biased features. The research question is something like focusing on performance issues, like how to improve the accuracy in a limited time or how to better solve the problem using human knowledge. So the objective is so biased, and therefore the user study is done in a very controlled, limited conditions. Like there's a lack of diversity in participants. For example, they are only designers, students, engineers, and their background, the knowledge, and the sense of purpose is shared in advance. So this means that the participants already know a lot about the machine learning and how to do the user study. So they are already prepared for the user study setting. But what we want to investigate is like more like on focusing end user investigation. Like do users deepen their technical understanding through IML experience? So we did a user study, which is done in a very highly flexible condition. Like we recruited participants from general public on the spot using the public space. And we set no performance goal, no explicit goal. And also the participants are allowed to use the system very freely according to their curiosity. So what we did in this study is we prepared basically IMS system for sound classification as an example, and we held a hands-on event in a science museum, which is in which the general audience gathers, and we recruited visitors there as participants, and we investigated the users' understanding and impressions through the interactive machine learning experience. So we prepared the interactive sound recognition system in which the participant can browse the data and create their own classification model. So the top half is the data exploration part, and the latter half is the model training part. In the data exploration part, there's a bunch of sound data embedded in the maps according to their similarity in audio characteristics. So the samples which share the similar sound characteristic are put closer and vice versa. So this is just like the Tillman's project. So the participant can browse the space to find the samples, find the audio samples to make it included in the training data. So by using the data or sometimes by recording their own own sound by playing YouTube videos, they can create a classification model in the latter part. So the flow is they prepare the training data, like defining category and record the actual data, and they train the model and they see the model performance in the bottom part. So this kind of very super easy and simple classification system we prepared. And in the user study, we collected data in the format of some questionnaires. So the first one is usability questions, which is about the a system's usage, such as you could understand what the feature map means, or you could use the sounds originally arranged in the map to train the AI or something else. And the second one is comprehension quiz, which is more like the general quiz of the machine learning knowledge. Like what do you need to make AI learn sounds, or how is the position of the recorded sound, the feature map determined, or what is a good practice to improve the performance? And we also ask them the confidence in their answers of the quiz items. And we asked some of them to answer the interviews. So to judge whether the participants actually understand the machine learning knowledge or not, we prepared some sample answers for each quiz items in advance. For example, for the quiz 1, we prepare answers like recording sounds, making AI memorize sounds, updating parameters of AI. This sort of simple answer is okay. So if the participant's answer is included in candidates' prepared answers, we regard the answer as correct and otherwise incorrect. And yeah, here's the result part. There are 61 participants in total, and about 67% of them had no previous experience in AI ML, just like the studying or developing AI or both. And only 3 of them had the experience of development. So first of all, let's see the overall trends. So to see the overall trend, I think they are very high in every item. For example, for every usability question item and comprehension quiz item, and also their confidence. And when we split the participants into 2 groups, that is users with the previous experience of studying or developing AI or without such experience. Yeah, there's some difference between the 2 groups, experienced groups and no experience group. About the usability test, the experienced groups scored higher, but about the comprehension quiz, in the middle part, surprisingly, the people without experience answered more correctly than the people with experience. So we are very curious about this issue. And when we see the concrete answers, the experienced participants sometimes made a mistake, some kind of technical mistake. For example, this is just an embedding map. So, for example, X coordinate and Y coordinate has no meaning. But some of the participants with some experiences answered like the X coordinate is frequency and Y coordinate is loudness of the sound, which is obviously incorrect observation. So yeah, this kind of incorrect understanding make their scores lower compared to the no experienced groups. And what we are interested in is the difference of their understanding or their impressions according to their usage of the system. So we cluster the participants based on their activities. Activities are composed of various elements like the amount of clicking, their total trial time, or the time spent on the map exploration, or these kind of the interaction logs are included in the activities and used for the clustering. So we cluster the participants into 5 groups using the hierarchical clustering. And yeah, these 5 groups have some tendencies. For example, this figure shows the x-axis is the total time spent. The horizontal axis is a total time spent for the experience. And the vertical axis is the ratio of time spent on the map. So if this number is higher, this means that the participants spend their time more on the map. And if the number is lower, they spend their time more on the classification part, the machine learning model development part. So for the 5 group, 1, 2, 3, 4, 5, group 1, 1, 2 are less active when we see the total time spent, but they focus on the map rather than the classification part. And the group 3 is obviously less active, and they focused on training validation, so model creation part rather than the data exploration part. And the group 4 and 5 are relatively active groups, and they focused on the model creation part rather than the data exploration. So firstly, let's see the group 1 and 2. Here the usability questions and the comprehension quiz and their confidence for the comprehension quiz. And their answer for the comprehension quiz, especially CQ2, which is related to the understanding for the map. This question is just like how the embedding is decided. The group 1 and also group 2 scored lower compared to group 3, 4, 5. Even though they spent most of their time on the map exploration. So this means that the time spent on the map is not always closely related to their understanding. And also this group 3, which is seemingly less active group, but yeah, they're focused on the model development part. Yeah, they surprisingly, they answered the questions very correctly compared to the other groups, even though their time spent is lower than the others. So we guess that this group is composed of smart users. They understood the technical points in a short time, or they already knew the technical points in advance. And about group 4 and 5, which are more active and focused on the model development part. For the group 4, they worked hardest to understand the system and the concept of the system. So the scores for the comprehension quiz not so bad. And the group 5 is not so bad about the CQ1, the CQ2, but about CQ3, which is question like something like how to make the performance of the AI better. They answered wrongly compared to the other groups. Yeah, they actually focused on the training, but they were bad at improving the performance according to the CQ3. So this result also indicates that their time spent for certain parts is not always relevant to their understanding. So yeah, this is quite interesting, implication, I think. And also we observed some, interesting, a behavior of the participants. For example, some of the participants intentionally created the detection model, even though our system is designed to make a classification model, which means that, for example, the P46 tried to create AI to detect a railroad crossing by explicitly recording a white noise as the second label. The first label is, of course, railroad crossing, ringing, and the second label is environment noise, white noise. So by doing so, when the railroad crossing rings, the percentage of the first class becomes higher, and they can use the model as a detection model. And another participant said that, for example, P58 said that she wanted to create an AI that takes a photo when cars not obstructing. So she also explicitly recorded the white noise, environmental noise, as a second label. And the second observation is that their interpretation for the map, which is based on the sound characteristics, but some of the participants thought the embedding is decided according to the semantic of the sound resources. For example, P12 said that sound of siren is close to musical instruments, while sound of trains is close to nature sound. And it's weird for me because the sound of siren and the sound of train is both the something we can ride. So the sound of siren means sound of ambulance. So both of them are something we can ride, but they are far away in the embedding map. So it's weird, the participant said. So this kind of misunderstanding happens for some participants. And another participant said that the men and women voices, they're totally far away, even though they are, both of them are humans. So it's also weird. So this participant also thought it as the like a semantic meaning of each sound resources is more important, more like influential compared to the sound characteristic, which is obviously incorrect observation. And finally, some of the participants created high quality training data by explicitly eliminating the irrelevant parts. So the participant 15 said that he wanted to classify dribbling sounds in basketball, so he excluded irrelevant parts, for example, shooting or some audience clapping. This sort of irrelevant parts should be eliminated. So he invented pre-processing without explicit intervention from us. So that's also interesting, finding. So yeah, basically that's it for the results. And the findings from the study is that firstly, overall the user experience, their understanding is good. So yeah, it's good thing to leave them to their own initiative because they are like very actively engaged in the IML experience without our guidance. And the second one is no-experienced people. People without experience scored lower in usability, so they had less confidence in the system usage, but actually answered higher in the comprehension quiz. So this means that, yeah, the experienced people were some sort of helped by past knowledge, while no people without AI/ML experience learned very honestly from their experience. And third one is there's some difference in the activities behaviors, and the difference in the activities means that there are difference in their interests. For example, some of them are interested in data exploration, while others interested in the model development. But this is not always related to their understanding. Yeah, for example, people explored well about the map, did not always correctly answer the comprehension quiz related to the map. This sort of difference, for this sort of gap, we should intervene in their interaction by teaching them some assistance, like this map is embedding map, and this data is embedded according to the sound characteristic, not the semantics. This sort of explanation should be necessary for them to correctly understand the technical points. And finally, we found some characteristic observations from some participants, even without our guidance or our advice. So yeah, they invented some interesting ideas without instruction, and they sometimes discussed the how to use the system with other participants or within the groups, for example, families or friends. Or this also affects their finding of the interesting usage. And finally, as a limitation of future work, the understanding classification is difficult, even with the map. Our purpose is by preparing the data visualization, it might become easier for them to understand the classification and other machine learning, some technical knowledge. But it's not enough this time. So we should prepare some different visualization, like drawing some decision boundary of the SVM, for example. And the second one is evaluation on the technical understanding is incomplete. Obviously, the comprehension quiz is not enough to measure their understanding. For example, the understanding is composed of many elements like programming skills, mathematical knowledge, or some their discussion of the topic. So we can measure their different abilities, different capabilities by preparing different metrics. So yeah, obviously CQs are not enough this time. And we can extend to other ML tasks. For example, recently the generative AI generation tasks are very influential in our everyday life. So we can prepare another opportunity for them to interact with some different models other than classification, like regression tasks or generation tasks, and see their behavior, see their reaction is also an important task as our future work. So yeah, that's it for my introduction. So if you are interested in the topic, yeah, I'm very, very glad if you see the full paper. Yeah, check out the content and give me some feedback through email or something. So yeah, please see the full paper for further details. And also you can see the event of the Science Museum, and also some video on YouTube. Sorry, this time I thought I can distribute some PDFs to you, and you guys can click the link afterwards. But sorry, just visit my website and you can find some YouTube videos and announcement of the event, so you can obtain some further understanding for our like event and study. So yeah, basically, thank you for your attention. That's it. Thank you.
Thank you very much. We got a couple of minutes to discuss. We're really it's close to 4, but we started a couple of minutes late, so we can stop a couple of minutes late, I guess. Any questions from the audience? Yes, Mar.
I am very curious because I must encounter that when I do interactive pieces and something, I am not very as an artist, and I don't like to do user studies, but I'm very curious because it was quite a nice user study what you did here. I should learn how to do this kind of user studies, and your questions were was a very direct user study, right? The questions were like these ones you ask, and how do you ask it them? Like, did you did they make you fill a form, or you ask them while they after interaction?
Yeah. About the data collection, we asked them to fill in the Google, questionnaire made by, and also some in-depth interview for the like agreed participants. Yes.
You did a semi-structured interview, or you make questions the same to each one?
This is basically semi-structured interview according to the comprehension quiz. So we asked them why they answered so for each comprehension quiz item. Like, how did you think? Why did you think so? So this sort of.
And you said that you had more that they did the big survey like questions, and then some of them you make this kind of interview. Do you select some participants for the interview?
Yes. If basically it's like a busy workshop, the participants are entering. Some of them are like going out, and why some participants showed some interest for us and asked us about why are you guys doing this kind of event or workshop, and this kind of like interested participants existed. So we asked them to spare their time, some of their time, and answer the interview.
But then they were quite fast. These semi-structured interviews, they were like on the spot. You mean in the workshop?
Yes. We couldn't spare much time for each participant, so it's done very quickly. Yeah, it's a very like a busy and some tough event for us. Yeah.
Okay. How long was the workshop, if I can ask the last question?
How long?
The workshop.
2 days, and for each day we prepared about 4 hours or so. So it's just held in one of the rooms in the Science Museum. So some of the participants visited our room after they visited some other exhibitions, and they're already tired. And
but the participants were not 4 hours. The participants were 10 minutes or 20 minutes, right? So
yes. That's a very short time for each participant. Yes.
Okay, thank you.
Thank you. So yeah, thank you very much. This was an exciting 2 hours. Let me at the same time sort of like try to wrap up and like make a comment regarding the last talk we saw. I think this is very paradigmatic, right? We live in a world where a lot of solutions have been found for finding similarity in images, question answering systems, and so on. But the user interface question is actually one of the most pressing, right? And one of the interesting things is like the study you have just seen is quite interesting. Like I imagine in a world where these interfaces, these maps exist everywhere. If you do the same study in 10 years, you will get a completely different result because people are so used to it, right? I mean, there was this Google Magenta project where you had this little rectangular device where you could put your finger on one of these maps and just sort of like navigate through the possible timbre space of musical instruments. Actually, a couple of weeks ago, we did a workshop on complexity aesthetics and data sonification at the Center for Interdisciplinary Research in Bielefeld, where we had the head sound designer from BMW, who at the day when he gave his talk, also had a presentation in BMW introducing the new generation of car, which has one of these maps on the center console, where you actually can sort of like select the sound landscape and timbre of your electrical car while you're driving by choosing a position on the map. And it's very similar. It's non-linear of like how this looks like. And if you imagine a whole population of people who are used to this, answering your questions versus a population who encounters such a map for the first time in the Science Museum, there will be a huge difference. And I think that is sort of like an exciting kind of world, like an exciting perspective for the future. Because just like we have, seen fantastic music coming out of harpsichords and pianos, which totally are not natural how they're laid out. They're like governed by the structure of what the technology behind the manual is, or what came out of the 808, the 303, the 909, these rhythm machines, which have like way too many buttons in front, but people engage with them for 30 years. And so in the same way, we're looking into a world where work is not just taken away from us, but the user interfaces, good and bad, that we have with machine learning and artificial intelligence will determine what will really be awesome in the next couple of decades. So in that sense, you're at the angle point of like our interaction with artificial intelligence. And this is really, really, really super useful. And I think this is sort of something which maybe is a last point. No matter what we do, like we can decide to not be practical, to just be theorizing in the humanities. If you go to a library, if you use a computer to enter text, if you sort of do anything, you do that via a user interface. And somebody thought about it, somebody tested it, and somebody made it better. And so this is sort of like one of the hidden dimensions of all the work we're doing. And in that way, it's part of cultural analytics. It's also beneficial for cultural analytics. And will also be the subject of cultural data analytics, which because there's different user interface designs. We already talked about this today. There's Japanese synthesizers, there's Berlin synthesizers, there's American synthesizers, for example. And so I think that is super, super exciting. So thank you very much for giving us this amazing insight into your work. As always, I have to not only thank the speakers, and Yusuke, thank you for the whole lab and everything, but also point to the next talk, which is in 2 weeks. And it's Peter Turnberg, simulating social media with large language models. So in some sense, this is like a reverberation of what we did 2 weeks ago. So yeah, thank you very much. And greetings to Japan.
Yeah, thank you for the invitation here.
Thank you so much.
Yeah.
Thank you.